In today's class, we will look at the background information which is required to understand the concept Hessian and its role in online learning. The background information what we have to understand is non-zero mean inputs, eigenvalues and eigenvectors, and Hessian matrix. What is non-zero mean input? Non-zero mean input refers to data or signals or forces whose average value over the time or across a data set is not zero. That is, the mean value is not zero. But if the inputs to the neural networks are non-zero mean, what is the impact that we are going to have? It is going to have an impact with respect to the learning dynamics. That is, if the inputs are not zero centered, the inputs to the deeper layers may become unbalanced, potentially causing slower learning or the convergence issues. And also weight updates. The non-zero mean inputs can make optimization landscape more complex, requiring more careful initialization and of the weights and then the learning grades. That is, non-zero mean inputs will have some impact. Therefore, we have to look how we can avoid or what are the measures to overcome this. Next is we will recollect what is meant by eigenvalue and eigenvector. Here you can see the matrix A, which is 2 cross 2, 1, 2, 2, 4, and the vector 1, 1. When we multiply A with X, we are going to get the matrix we are going to get the vector 3x, because it is 1, 2, 2, 4 and then 1, 1. When we multiply, we are going to get, that is 1 plus 2 and then 2 plus 4, which is going to become 3 and then the x. Now when we plot this 3x and 1, 1, you can observe with respect to 1, 1, 3xx is scaled and also rotated. Now similarly, when we multiply 1, 2 and 2, 4 with vector 1, 2, what happens is we are going to get the vector, that is 5 and then the 10, but this vector when which we have multiplied 1, 2, that is going to replace this 1, 2 vector with scaled value, but it is not rotated. A vector that undergoes pure scaling without any rotation is known as eigenvector. The scaling factor is known as eigenvalue. In this case it is 5, because 1, 2 to become 5, 10, the scaling factor is 5. That is, we know this eigenvalue and eigenvector equation, that is ax and lambda x. Eigenvalues are represented by lambda. Next, we will understand Hessian matrix. Hessian matrix of a multivariable function f of x, y, z organizes all the second order derivatives in a matrix form. That is, if I take the way with the variables function with the variables x, y and z, then the Hessian matrix will have the first row will be the second order partial derivative of x with x, and next second order partial derivative with x with y, x with z. Next, similarly, second row will be the second order partial derivative of y with x and y with y, y with z. It keeps continuing for all the variables what we have. We'll understand how we are going to compute the Hessian matrix. Let us take the example, a function f with x and y with function as x cube minus 2xy minus y to the power of 6 at the input point 1, 2, what we are going to get. Now when we compute this function partial derivative with respect to x, that is x to the power of 3 minus 2xy and y to the power of 6, we are going to get 3x square minus 2y. Similarly, when we take this partial derivative with respect to y, we will get 2 minus 2x and minus 6 to the power 6 y to the power of 5. And now after getting, we will do the second order partial derivative, that is x with x. first function what we had, that is 3x square minus 2y, which is going to become 6x, and x with y is going to become minus 2, and then y with x, similarly the same case, that is if we take minus 2x and minus 6y which we got here, we are going to get minus 2, and then y with y, if we take this function and then do, we are going to get minus 30 y to the power of 4. And now our Hessian matrix for this function will be given with the second order partial derivatives of x with x in the first row, and then y with this can be also x with y, and this can be y with x and y with y, which is we are going to get 6x minus 2 and then minus 30 y to the power of 4. This is the Hessian matrix in this case for this function. Now when we take the second order derivative on the function, what is the information we are going to get? It is going to become the curvature, because when we do that one, the sign of the derivative is going to tell us whether the slope is increasing or decreasing. In this here you can observe, if the second order derivative of a single variable function value is less than 0, the slope is going to decrease. But the second order derivative of a single variable function x, if its value is greater than 0, then obviously the slope will be slope will be increasing. That is, the second order derivatives gives us the information about the curvature, and the signs will help us to classify the points to find out whether the slope is increasing or decreasing. As we know, first order derivative is a vector or a gradient we are going to get, but second order derivative is a Hessian matrix, which we are going to arrange the second order partial derivatives of all variable combinations in that function. That is, summarizing, first order derivative of the error function with respect to the weight is a gradient, which will give the directional update, and we use the backpropagation algorithm to update the weights. That is, first order derivative is used to determine the direction and the magnitude of the weight updates, but second order derivatives is given by dou 2 of E by dou 2 dou of W square is a Hessian matrix, which gives the curvature, and we can use it is used in the Newton's method, and it will determine the curvature of the error surface to find out whether what is the concavity or convexity of that surface. In neural networks, training involves minimizing an error function with respect to the network. That is, always we have to minimize the error with respect to the weights. Therefore, the derivative of the error function with respect to the weights is a gradient dictates the direction to update the weights to reduce the error, while eigenstructure of the Hessian matrix reveals the geometry or the curvature of the last surface, guiding how quickly or slowly the optimization converges. This is the what we have to observe with respect to first derivative and the second derivative. First derivative is going to give the gradient, but second derivative is going to give the eigenstructure of the Hessian matrix. That is, now going in detail, derivative of the error function with respect to the weights, that is given by dou E by dou W. That is, derivative often this is going to be defined by delta W with respect to E is a vector of the partial derivatives with one component for each weight in the network. For every weight, that is, we have W1, W2, then we have the delta of E with respect to W1 and delta of E with respect to the W2, and it will be calculated using the backpropagation algorithm. That is, derivative of the error function with respect to the weights, it represents the direction of the steepest ascent in the loss landscape, and the role in optimization, that is in the backpropagation or the gradient descent, that is old weight will be subtracted with the learning rate multiplied by the gradient what we got. That is, we have to move in the opposite direction or the negative gradient to find the local minima. And in the backpropagation, we know That is our chain rule. We'll find error with respect to the out, and then out with the net G, and the net with respect to the weight. That is OJ is the activation output, that is the output what we are getting after passing to the activation function, and the net, what is the net input we have got. And now coming to the eigenstructure of the Hessian matrix. Hessian matrix is a matrix of second order partial derivatives of the error function with respect to the weights. Therefore here dou 2 of E by W, dou 2 of Wi and Wj, because more than one weights will be there. That is, if you have two weights, then it will be dou 2 E of dou W1 and W2 actually. The eigenstructure consists of the eigenvalues and then the eigenvectors. That is, the eigenvalues determine the curvature of the loss function in the direction of the eigenvector. We have to look at like what is the role of the eigenvalue and the eigenvector. Eigenvalues will determine the curvature of the loss function in the directions of the eigenvector. Positive eigenvalues indicate the convex value, that is upward curvature. Negative eigenvalues indicate the concave or ridge, which is a downward curvature. Near zero eigenvalues, that is, if we have almost the values which are at this point, or whether the points are here, the indicates the flat region, and we are indicates, that is, we are at the optimal, whether it is a local minima or the global maxima. That point it is going to indicate if the eigenvalues are near zero. That is, in the Hessian matrix we have to look at what is the role of positive eigenvalue, negative eigenvalue, and then the near zero eigenvalue. That are principal directions, that is eigenvectors. The eigenvectors represent the directions in the weight space that corresponds to the principal curvature. Hessian based optimization, or the Newton's method, the update rule will be what? New weight will be old weight minus H inverse Hessian matrix, and then the derivation what we got of the weight with respect to the error, that is, uses the Hessian to adjust the steps, taking larger steps in the flat directions and then smaller steps in the highly curved directions.